Chapter 3 of the Cormen et al. Textbook includes, in the back, a discussion of functions often found in analysis and identities involving those functions. And today I'm just going to review briefly the ones that I find myself using most often. I encourage you to read the chapter so you're aware of what's there. Often we need to be able to make claims that depend on whether a function will ever increase or decrease. And so we need these definitions. A function is monotonically increasing if whenever a parameter m is less than n, then the value of the functions will also have the same relationship. And similar, decreasing if the other relationship holds. Strictly increasing if whenever you give it a bigger argument, the value that you get out of it will be bigger. And same for decreasing. Okay, now let's look at polynomials. We know what polynomials are. For example, 3n cubed plus 2n squared plus 15n plus 37 is a polynomial. And we say this polynomial is of degree 3 because the largest exponent on the variable that we're writing the polynomial in is 3. So this fact here simply says that for any polynomial, it's going to be theta of n to the d, where d is the degree of the polynomial. So whenever you see an expression like this, you just look for the biggest exponent. You know, if this was n to the 3.1, then this would be theta of n to the 3.1, and so on. Next, quite often we deal with exponentials. First of all, in relation to what we just talked about, polynomial, n to the b is a polynomial, but a to the n will always grow faster. This is little o, so that means that n to the b eventually will be overwhelmed by a to the n for any real constants a and b, where a is greater than 1. So any exponential function with a base greater than 1 grows faster than any polynomial function. So you can have n to the 100 or to the 1000, whatever, but this is still going to have a slower growth rate eventually. In other words, it's going to be little o of 1.1 to the n. Will eventually grow much faster. Now let's look at some useful identities used quite a bit. Something to a negative exponent is 1 over that number. If you multiply a by itself m times, and you multiply that by itself n times, then just think about, writing out a m times and then writing that string out n times. Of course, then you're going to be writing out m times n a's. And a similar fact, if you write out a times itself m times and a times itself n times, multiply those two, you're going to write out m plus 1 a's. So now let's look at logarithms. The simplest version of what this is saying is that if you take the log of n, it's always going to have a slower growth rate than n to any positive power. N to the 0.5, for example, will have a higher growth rate. And this is also true when you exponentiate the log. So even if you multiply the log of n by itself some constant number of times, which, by the way, is notationally written this way, then that's still going to be little o of n to any positive exponent. So logs grow slower. That's why it's nice to have algorithms that have logarithmic growth. They're a lot more efficient than many other algorithms. Let's now take a look at some identities involving logarithms. First of all, perhaps we should have started with this. This is the definition of a log. The log base b of a is the number to which, if you raise b to that power, this whole thing, you get a. That's just the definition of a log. So you should be pretty comfortable with this. Moving down a little bit here. This identity here shows us what we can do with base changes. So if we have log base a of n, then we want to change the base as some other base, then you just write out the other base and divide it by log of the other base of a. So for example, if we have the log based 10 of n, then that's going to be equal, and we want to change it to 2, log base 2 of n divided by log base 2 of 10. Now notice that this is a constant. So the difference in growth rate between logs is just the difference of constant. In particular here, 1 over log base 2 of 10 will be the only difference in growth rate. And being a constant, that doesn't grow. So that's why we generally treat all logs as being in the same category, although, of course, there is a difference between log base 10, log base 2, log base d. But from an asymptotic point of view, they're all in the same category. Okay, here's another nice identity, in fact, with an important history. The log to some base of two numbers multiplied by each other is the sum of the logs of those two numbers. And the reason I say ask your slide rule is because this is the basis for how slide rules work. I don't know if you know what a slide rule is. This is kind of old history. Some sticks that you slide back and forth to do math. Basically, they are converting multiplication problems to addition problems. It's also a shorthand way that was used to do math before we had calculators. Here's another manipulation that's often useful. If you have the log of something to an exponent of power, you can just pull that exponent out in front of the expression. This just helps you simplify some things. The log of 1 over a number is a negative of the log of that number in a given base. And if we want to flip what's the base and what the log is being taken of, we just make it a reciprocal. So log base b of a is 1 over the log a base b. This one I see come up occasionally. If you have a variable to some log of two other numbers, you can switch what the number is that you're taking the log of and what is getting the exponentiation. Next, we'll look at factorials. Of course, you remember that a factorial, n factorial is n times n minus 1 times n minus 2 times 1. And factorials are pretty bad. If they show up in analysis, it's not good news for the efficiency of an algorithm. They grow faster than exponentials. In other words, this is little omega, which is the flip side of little o. A factorial grows strictly faster than 2 to the n, which is already really bad. You don't want algorithms that are 2 to the n. This is even worse. But there are even functions that are worse than that. A factorial itself grows less fast than n to the n. So we're building up a little hierarchy here of badness. We had the log n, and we found out, of course, that grows less than exponentiation, like n to the b. 2 to the n is worse than that, and n factorial is worse than that, but n to the n is worse than that. And we should also note that the logarithm of a factorial brings it down to theta of n log n. Finally, there's the Fibonacci numbers, which show up an amazing number of places in nature. It's very strange. So the first Fibonacci number is 0, the second Fibonacci number is 1, and then all the Fibonacci numbers after that are the sum of the previous two Fibonacci numbers. So the next one would be 0 plus 1 is 1, the next one is 1 plus 1 is 2, and then 2 plus 1 is 3, and 3 plus 2 is 5, and 8, and 13, 21, and what's that, 34. You can see they're growing. Eventually they kind of start to build momentum, and they grow exponentially. Well, that's it for the common functions and useful identities and the end of part 3.